Okay, so we are recording now, and let me send you to practice quiz 2.5 is a section. We're going to be doing two sections today, 2.5 and 2.6. Both are very smaller, quicker sections. I noticed that there is a post on number 50 to go over, and a couple comments. The homework, it's kind of evolving, my strategy with homework, and what is kind of turning out is I'm giving what I'd like to give is 10s on the homework, and 10 out of 10. But if there are things that I'm finding that are mistakes or things that are incomplete, I am giving people feedback on that, and then they can update their homework and then get their 10 on that. So that's kind of the strategy I'm going to wind up using. So if you've got, check your homework. Particularly if there's no grade on it, there'll be comments on what you need to do, and then I will check it. I'll wait till next weekend. Next weekend I will be grading the new homework and going over all the checks from the previous week. And so you have really by the next weekend to, by let's say Friday morning, to get the updates in.
Okay, thank you.
Questions on that or comments? Okay. And also you'll notice in our schedule that we have exam number 2 at the end of this week. And there's no take-home portion. There's really no support given for any one of these exams except the very first one and the final exam. So the first one had a take-home portion. I strongly believe in letting people kind of know what it's like to study well for an exam and be well prepared. And so that hopefully you had that as your experience on the first exam. And then it's up to you to be well prepared for the second exam, which is this coming Thursday. And then as we get close to the end for the final exam, I'll have a review assignment that you'll do, and then you'll turn that in before the final exam. Any questions on any of that? All right, if there's no questions, then let's go to number 1 in the practice quiz. Which is a vertical asymptote and which is a horizontal asymptote between A and B? And then draw a picture representing each of those situations. A and B. So this week, since we have an exam on Thursday, I want the updates on the homework. So the homework that you had already turned in. If you didn't get a grade on that, have that in before the exam on Thursday. All right, does anybody need more time? If not, let's go ahead. So, I accidentally hit some buttons on my, yes. I have it's called a pen with a Wacom tablet, but it's easy to hit a button on the pen and then it changes things how it works. All right, so as x gets larger and larger, the f of x is getting closer and closer to 3. So the function might be something like this. And that is a horizontal asymptote. And the other one looks like this. As x gets closer and closer to 3, but from both sides. It's implied because there's no plus or no minus. This thing gets closer and closer to infinity. So you have to have it from both sides going up to infinity. All right. Give me a brief amount of feedback in the text channel, how you are with number 1. Yep, I started the recording. All right, let's go to number 2. For a function f of x, describe the difference between a tangent line and a secant line. And what does each represent? You can draw a picture if you want. It's not necessary, but it might be helpful. And quick question. Has anybody looked at the videotapings recently, and did they notice, is it a little bit better since I turned up the resolution? And is it adequate now? Or should I experiment with turning up the resolution even more at the danger of maybe having some glitches? Okay, if you haven't looked at the videotapes recently, next time you do, if you could just give me a little feedback, I'd appreciate that. All right, anybody need more time? All right, let's look at tangent line. Let me go back to here. You need 2 points. Secant line, you only need 1 point.
Is it the other way around, Mr. Shankin?
You are exactly right. Thank you very much. Tangent line is 1 point, and this is 2 points. Thanks, Bianca. And so if we have our function, maybe that's my function f, and here are my points, and here is a secant line, and here is a tangent line. And the tangent line represents the instantaneous slope. And secant line represents the average slope. But instead of using the word slope when we're doing represents, that would be a poor choice of words, because instantaneous rate of change, because it's what it means. Slope is not a word that tells you what it means, it's kind of a technical math term. Average rate of change. Okay, now come back, give me feedback. This time I think most of you already got this idea, but give me feedback on, did you need review on it? Was reviewing this helpful in a practice quiz, or no, not necessary? Don't need the review, or it's helpful? Okay. All right, let's go to number 3. Find that limit, and you do it in this order. First of all, do it with a table. And you have to construct the table that makes it clear what the limit is. And then you do it with a graph. You can use like Wolfram Alpha, graphing calculator, or whatever. And then make it clear, quick diagram. Like if this was on a test and I asked for this, you'd have to reproduce that. Even in the homework too, if it says, find the limit using a graph, you not only have to put it into a graphing calculator or computer, you also have to make another rough sketch of it on your paper. It can be a very quick rough sketch, but it's got to verify and show me how you used the graph to get your answer. And then do it algebraically. You should be getting the same answer all 3 times. But all 3 statements need to be clear that how you're getting your answer. verify this with me. The way I think Canvas works is when you upload an assignment, it's in there, and then when you upload a second time, let's say because it's your final draft of your homework, it just replaces your previous upload with the latest upload. Is that correct?
Yes, that's correct.
I'm pretty sure that's the case.
Okay.
Uh-oh, if that's the case, I thought it was saving it, so I might have goofed up on mine.
Oh, okay.
Have you noticed, Professor, if it preserves earlier drafts for you in the back end?
What I'm noticing is just that it's correct for most people. Most people have the correct thing uploaded. So I'm not seeing it on there.
And you only ever see one. You see multiple drafts.
Correct. I only see one.
Professor, this is Dominic. I just want to let you know that on my homework, my corrections, I added them all to my 2.3. I thought I was saving time, but hopefully it didn't.
So I looked in 2.3 to find all your corrections for many assignments.
Well, you'll find my corrections for 2.2 and 2.3.
In 2.3.
Yes, sir.
Okay, I'll make a note. of that. Thank you.
Thank you.
And reminder, group leaders, make sure everybody knows for each group who the spokesperson for today is and have that rotate each day. All right, anybody need more time on this problem? Number 3. All right, let's go. And I'm going to cheat. I told you to do it in this order. I'm going to do part C first. And this part is this, and so this and this are going to cancel, and it equals x plus 2. So that's all you're going to get. So when you make a table, if I put 1.9 in here, all I'm going to get is 1.9 plus 2, 3.9. But if you plug it into this function, you will get 3.9 out. This is just a short way of getting there. And 1.99 is going to be 3.99. You're not allowed to put 2. You put 2.1, 2.01, and then you're going to add 2, 4.1, 4.2, So as we're squeezing in on 2, this right-hand side is squeezing in on 4. So it looks like the limit is 4 from looking at the table. All right, now it is very beneficial to have these things in the X column here arranged like this so that it looks like we are squeezing in on the one number you're not allowed to put 2, and thus this squeezes in on the result 4 like this. This can be a challenge for some students that they have to work on that because they tend to not get these in the right order, but it's worth practicing on that. It makes a table really clear. Yeah. And to get full credit on an exam, I'm going to require that you put these in this kind of ordering. Okay. And then for graph, you do y equals x squared minus 4 over x minus 2, and I'm just going to pop over to Wolfram Alpha. Which is being a little bit slow. And I just hit enter. And you see there's the function. Y equals x plus 2 is what it's graphing. Now, it should be putting a hole. When x is 2, there should be a hole right there. But it's not doing that because it's not smart enough to figure that out. It just plots a bunch of points and connects them in a line. But as we get closer and closer to 2, this is going to get closer and closer to 4. So if we come over here, what you would need to reproduce is that picture again over here. So here's my function. Y equals x plus 2. And then as we get closer and closer to 2, the output gets closer and closer to 4. And that's kind of showing it visually with a graph, and then algebraically we've already done that. All right. Again, this is one that I think you know. Give me a little feedback though. Is review helpful on this? Or could you skip the review? Okay. And let's go to questions on homework. And the question that was up before was number 50. So I'm going to start with that one. And let me insert a bunch of space here. And let's go. Number 50 is on page 90. Okay, so I'm going to let's go to snipping tool. I'll take all the instructions as well. All right, so find all vertical asymptotes and then do more. All right, to find the vertical asymptotes, I would factor out the denominator. And my initial instinct is that x equals 0 is a vertical asymptote because it causes the denominator to be 0. And x equal 8 is a vertical asymptote because it causes the denominator to be 0. But that may not be correct. It turns out that they will only be vertical asymptotes if this factor doesn't cancel with a similar factor in the numerator. So I have to go up to the numerator and factor that out. Now, when I factor out the numerator, there's an x common. And then that x, and then these are going to factor. X. Now, the two things have to both be minus. To multiply to be a positive number. Two things that multiply to be 16 and add to be 10 are 8 and 2. Alright, now we see that both numerator and denominator, both terms reduce. And all I'm going to get is this. So this does not have any vertical asymptotes. And so vertical asymptotes, none. So we're doing number 50. And then it asks us to find, if there was a vertical asymptote at x equal a, then we'd have to find the limit as x approaches that a from the right and from the left. But there is no such a, since there's no vertical asymptote, so I don't have to answer any of the three questions over there. Now, what this function is going to look like this. It has a y-intercept of -2, slope of 1, so it looks like this. And at x equals 0, there's going to be a whole discontinuity. At x equal 8, there's 8 over 6 up, there's going to be a hole over here as well. But the limits still will be fine. As x gets really close to 0 from the left and the right, it'll approach -2. Because remember, you're not allowed to reach your destination, so it doesn't matter what happens at those points. All right. Is that all clear on number 50?
So there's no limit because no asymptote. It's just a hole. Like if there was a limit, there would have. I mean, if there was an asymptote, there would be a limit.
That's correct. Wherever the asymptotes are, those are a's. And so, like if there was a vertical asymptote at x equal 3, then you have to find the limit as x approaches 3 from the right and as x approaches 3 from the left and so on. But if there's no vertical asymptote, there's no a, so none of these questions make any sense. All right, other questions on homework. Number 48, 46. All right, well, let's...
The wording of number 50 threw me off.
Okay, Okay, let's start with 46.
36.
All right, well, actually, 48, we already have that one. It's right here. So let's do 48. I'll do it in red. This is equal to cosine of x divided by x plus 2. All right. So the vertical asymptotes, there's two of them, at x equals 0 and at x equals negative 2. So we have to find the limits. This is for 0 and for 2. We have to answer these three questions. So let's just do for 0. When x is equal to 2, we're going to find the limit as, well, let's say as x is 0. As x approaches 0 from the right of that function f of x. Now, as x approaches 0, what happens is the numerator, let me jump over to green for a minute, the numerator is going to get closer and closer to 1. And
Let me go out again.
and then the denominator, as x gets closer and closer to 0, this thing gets closer and closer to 2. And as x gets closer and closer to 0, this gets closer and closer to 0. Now, what this does is this drives the whole fraction to infinity, and the only thing that could be negative is this 0 thing, but it's driving it to 0 from the positive side. I'm going to put a little plus there. And so this is going to go to positive infinity. And as we go to 0 from the negative side, if this was a minus up here, we would have gotten negative infinity, because this would have still gone to 1, this would have still gone to 2, but this would have been a small negative number over here. So that would have been negative infinity. And then the total limit as x approaches 0 does not exist, because they're two different values. One is positive infinity, the other is negative infinity. And then you have to do this for as x approaches negative 2, from the left and from the right, to see if it's going to positive infinity or negative infinity. It'll go to one or the other, since it's a vertical asymptote. And if they both go to the same thing, then the last limit exists. Otherwise, it doesn't exist. All right. Does that clarify things for number 48?
Yes, it does. Thank you.
Okay. And then number 46.
So I just had a quick question
Yes.
about the cosine of x.
Mm-hmm.
So I know cosine of 0 is going to be 1, right? So when it's cosine of negative 2, that doesn't exist, right?
It would be negative 2 radians. So let me pull out my calculator. And I'm going to make sure that my mode is in radians. It was in degrees. I'm switching it over. And I'm going to go cosine of negative 2. And I get negative 0.416. Alright, so it's going to be a negative value. So The end result of a cosine can't be negative 2. But this is cosine of negative 2. So that can exist.
Okay. So you just use that value and then
That's what the numerator
Yeah.
is going to be. The value of it isn't so important as that it's negative. That's going to be important.
okay, all right.
Yes. All right. All right. So let's go to 46. All right, analyze the following limits and find the vertical asymptotes. All right, so I am going to go here. This, first of all, there's an x squared common. Squared minus 49. So the top becomes x plus 7. The bottom becomes x squared. X plus 7, x minus 7. And then the x plus 7s cancel out. I accidentally pressed a button on my pen. Okay, so then this becomes, let me, get rid of some of those squiggles. So this becomes 1 over okay. So now I can look at these questions. As x approaches 7 from the left, so x would be something like 6.99. If x is 6.99, I'm going to get the top is positive, x squared is positive, but x minus 7 will be a really, really small negative number. It's going to make the whole thing go to negative infinity. So that's going to be A. For B, as x approaches 7 from the right, I would use something like 7.001. And then everything is positive, including that little tiny number. So this one is going to go to positive infinity. So since they're two different values, x approaches, if they asked as what is as x approach, the limit as x approaches 7 without a plus or minus sign, we would say it does not exist. But they don't ask for that. They then say the limit as x approaches negative 7 of f of x. As x approaches negative 7, well, the top is going to be 1. The bottom is going to be 49, negative 7 squared. And then negative 7 minus 7 is negative 14. So you just get that value. And you punch it out in the calculator, and that would be your final value for C. And then for D, as x approaches 0, all right. As x approaches 0, it depends on whether it approaches from the left or from the right. You're going to have small negative numbers or small positive numbers for x. Now this, when x is approaching from 0 from the left to the right, is not going to affect x minus 7. X minus 7 is still going to be approximately negative 7. But x squared, well, we're fortunate that it's x squared. When it's x squared, you're going to get positive. So you're going to get 1 over a positive number, really small positive number, times a negative, so it's going to be negative, really small number. So this is going to be negative infinity. and part T. Any questions with 46, or is everybody okay with that?
I'm good with that.
All right, and what else was there? Somebody had mentioned one verbally. I'm forgetting what it was. All right. Any other questions then? All right. Well, let's go on to limits at infinity. So we got two sections today. First one. So notice the slight difference in the titles. 2.4 was infinite limits, and 2.5 limits at infinity. 2.4 was vertical asymptotes. 2.5, we're going to see this is horizontal asymptotes. And notice how they use slightly different wording for those two cases. All right. So we start out with a definition. The limit as x approaches infinity of f of x equals L. Now, let me put this in contrast. The practice quiz today. We had two different kind of limits. When the infinity shows up underneath the limit, then you're saying what happens as x gets super, super large? And that's a horizontal asymptote. When the infinity doesn't show up until the right-hand side, then you're saying, that's what the heights are doing. As x gets super close to 3, the height of the function f of x goes on up to infinity. So this is this type that we're at right now, which the infinity sign is below the limit as x approaches infinity. So the limit as x approaches infinity of f of x equals L means that the values of f of x can be made as close to L as we like, no matter how close, by taking x sufficiently large. If you take x large enough, you can get as close as you need to the limit L. So let me just draw a quick picture here showing what this is about. So if I have as x is getting closer to infinity, means you're getting bigger and bigger inputs. L then must be here. And as x gets super large, this function could be doing lots of things. It could be going here, 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 but as it gets super large, it gets super tight to this. It gets incredibly close to the dotted line. Infinitely close. And it keeps getting closer and closer and closer to that. And I'm going to change the situation here, and we're going to look at some values over here, but just before we look at some problems, I'm going to do a little review in case it's been a while since you had horizontal asymptotes. One of my favorite examples of explaining horizontal asymptotes is a company that I don't believe in their product. I'm a vegan and I don't eat McDonald's food, and in general fast food and processed food is I think the a huge problem in our country. But McDonald's revolutionized fast food. In fact, they were the ones that really made the whole idea of fast food. And let me get a little space here. And all right, before McDonald's, a quote fast food restaurant wasn't really fast food. You'd go in and you'd say, give me a hamburger, and then they'd cook it up, and 10 to 15 minutes later, they'd hand you the cooked hamburger. They were the first ones that decided they would pre-cook the food so that when you ordered it, they'd already have one ready for you and they could just hand it to you. So fast food became really just what its name was, really fast food. In order to do that, though, they had to have a really limited menu. Every single item that they made had to sell lots. They couldn't afford to have something that very few people would order, because then you'd have that hamburger pre-made and nobody would order it, and after 2 hours sitting there, it's no good and they got to throw it out. So they had to really be scientific about every item on their menu. And so they do it very often with marketing in a town that they think is or a city that's a good representative city for the whole of the United States. It has ethnicity and age distribution, much like, and eating habits, much like the rest of the country. And so they'll introduce, let's say, a new hamburger in this place. And so they would then, in that one city then, they might put up lots of billboards and do lots of advertising for this new hamburger, and then see if people are actually going to go for it. So they might do some promotions where, it's at a big discount when they first start eating it and so on, and then see if people will reorder it. So if we have on the x-axis, this is dollars spent on advertising. And on the y-axis it's the new hamburger. So they really are advertising this new hamburger, and here's the new hamburger sales. All right. Now when they first start, they just put it on the menu, and a few brave people try it, and so it winds up being this much sales right here. But as they spend more in advertising, they get more and more sales. It's going up like this. What would you expect this graph to look like in the long term, over time? So everybody take a moment in your group and try to decide what is the eventual shape of this graph going to be like if you keep raising advertising infinitely high. What's the general shape of the whole graph? I'll give you a quick minute to talk that out in your group, and then I'll pick on the group in a minute. Make sure each group knows who the spokesperson is. All right, group 4. What's the shape?
Like, it would look obviously
Identify
like.
yourself, please. Is this Sally?
Yep, it's Sally.
Okay, great.
It would look like the square root graph, just getting infinitely like close to that like peak and just like slowing down there. Like the more you raise the advertising.
Okay, like the square root graph, going like this. The steepness gets smaller and smaller and smaller. Okay? Everybody agree with that? Is there anybody who disagrees with that? You're mostly correct, but there's one thing that you're not correct about. Does anybody see it?
Wouldn't it just keep continuing on that height eventually and then get closer and closer to a certain height?
That is correct. It will wind up, because the square root function gets infinitely high. Takes a long time, but it gets to go infinitely high. The difference between this and the square root function is that this is going to have a horizontal asymptote. And this will never get above that. It'll get infinitely close to that. It's kind of like advertising saturation, where it's just not going to do any more good. We see natural limits form in lots of things like this. We see this in, if you put cells in a petri dish, let's say bacteria, and then they multiply. They will have exponential growth. They'll grow really fast. You can start with just 2 cells. They'll grow really fast, but as they get what's called near the carrying capacity for the petri dish, there's just so much that this petri dish will hold. They'll wind up getting a vertical. Almost everything that we know of that has exponential growth has also a horizontal asymptote. Could be a carrying capacity. There's one thing, though, that we know of that has exponential growth, that has no horizontal asymptote, and that's because it's a creation of our mind, which is money. Money, you invest it, has exponential growth, and there appears to be no limit, and then we just can print more, and it seems to be the one exception.
I mean, you could argue there are asymptotes there. We just keep sidestepping them or like changing the goalposts.
For money, you
Yeah.
could argue, yes, because you could say that, they've changed the rules. There used to be a gold standard that you had to have all printed money have gold behind it. And then they changed the rules and said, no, we don't have to do that anymore, and so on. All right, so horizontal asymptotes are natural ceilings. Horizontal asymptotes also happen on the flip side. When you take something, and let's go here and get a little more space. When you have extermination happening, so you have a population that wolves, and there's just not much of an environment for wolves, and they get lower and lower in population, and they can do something like this. They might actually go extinct, except that we might, preserve have a few preserves, etc., and they're real small. We could do the same kind of thing with insects in our house. Maybe we have ant problem, and then we put down insecticide, And we never quite get rid of all the ants. They're kind of transient beings. They kind of come wandering through. But the more and more insecticide we put down, the less and less ants that we have over here. All right, so those are some kind of orienting facts about horizontal asymptotes. And we use calculus terminology of limits to describe them now. And notice how the infinity comes underneath the limit sign.
I have a question.
Yes.
So I remember taking a trigonometry class, and you said that there are some cases where the function can cross the horizontal asymptote.
Very good. I was going to mention that, and I forgot
Well,
to mention
aren't
that.
those slanted asymptotes?
We can get to slanted in a minute, but let's just talk about crossing, vertical or horizontal asymptotes. Turns out, vertical asymptotes, you never can cross them. If you cross a vertical asymptote, then you've assigned a value. So when, like, you know, if the function has x minus 3 in its denominator, then you can never let x be 3. But if you cross that vertical asymptote, you've assigned a value, so you never cross a vertical asymptote. But horizontal asymptotes can be crossed. And look at this one right here. We see that we're crossing the horizontal asymptote here, here, here. In fact, sometimes functions even do this. They oscillate around it, but get smaller and smaller oscillations as you go around it, like this. Horizontal asymptotes are not sacred like that. In fact, if it's carrying capacity in an environment, suppose we got to carrying capacity of planet Earth with people, we might have a whole bunch of pregnancies, pregnant women that send us over the carrying capacity, and then we can't feed everybody, and so then we lose some population, and then this would be a really bad case scenario for humanity way in the future. But you can see how we might go above and then slightly below and so on for the horizontal asymptote there. It's not sacred crossing those. And then Kylie is also mentioning the slant asymptote. Slant asymptote, we'll briefly describe that later, but the main two are, let's not go to slant asymptotes yet. The main two we want to just focus on is vertical asymptote and now horizontal asymptote. And did I clarify your issue there, Bianca? Thanks for bringing that up.
Yeah, you did.
Okay, good. All right, so let's look at some problems of when we have horizontal asymptotes. As x goes to infinity, this first one. As x gets super large, let's suppose x is 100, and then 1,000,000, and then 1,000,000,000. Well, the numerator is staying stuck at 7, but the denominator is getting larger and larger and larger. This whole thing, the fraction is getting smaller and smaller and smaller, and is clearly going to 0. So that's the basic idea for horizontal asymptotes, and that would be kind of an extermination type thing with the wolves, like this, or with insects. All right. When the denominator keeps getting larger and larger, while the numerator is either getting larger more slowly than the denominator is getting large, or is just being stuck, like it's stuck at 7 right here. All right. The second one, which got renamed number 1 again, as x goes to infinity, what is the horizontal asymptote of this one? Anybody want to chime in? What is that horizontal asymptote?
Well, as x approaches infinity, the function just gets larger and larger, so it appears that there isn't one.
That is correct. This, instead of saying equals, we just say it has no horizontal asymptote. The only ones that have a chance to have a horizontal asymptote is fractional ones. If it doesn't have a fraction, it has no chance. And this clearly is going to go off to infinity as x goes off to infinity. All right. Well, let's look at number 3. As x goes to infinity, now this one is different than number 1, than the first number 1, in that the numerator is also getting larger. The numerator is getting larger, but the denominator is getting much, much larger than the numerator. And when I'm in pre-calc, I do this, and it probably is worthwhile reviewing this real quick. Let's go to let's go here. Type in if x is 1,000,000, how much larger is x to the 43rd than x to the 42nd? If x is 1,000,000, x to the 43rd and x to the 42nd seem both gigantic. But how many times larger is x to the 43rd than x to the 42nd?
1,000,000.
That's right. It is 1,000,000 times larger. Now, when we do a rough approximation, if somebody asks you, what is approximately 1,000,000 plus 1? You don't tell them, well, it's approximately 1,000,001. It would be more like a town, a city's population is 1,000,000. And then one person moves in, you don't say the population is now 1,000,001. If their first number was just an approximation, when you add another number, you'd still keep it the same. 1,000,000 plus 1 is approximately 1,000,000. And when you take, if x is 1,000,000, x to the 43rd plus x to the 42nd is approximately x to the 43rd. This number right here being so much smaller than this one, the answer is just the bigger one when you add them together. So that's what's going on in horizontal asymptotes. It's why in horizontal asymptotes, we only, if we're trying to say what's bigger, the numerator function or the denominator function, we only have to concern ourselves with the leading term of each of those. You only have to look at the leading term here, and all the rest become insignificant when x becomes really large. You only have to look at the leading term here, and everything else becomes insignificant when x becomes really large. When you add or subtract things of vastly different size, your approximate answer is just the bigger one. And so we just compare the degree of the numerator to the degree of the denominator. So on number 3, we notice that this is first degree over a third degree. So first degree over a third degree polynomial. And so the higher degrees in the denominator, that one, when x becomes really big, that one becomes so much bigger than the numerator, and this whole thing goes to 0. All that is comparing degrees to see which one gets larger faster. And because these things, the 7x becomes basically inconsequential, you can think of this x and this x cubed reducing. And you wind up just having really an x squared in the denominator. And even the coefficients, the 3 and the 25, become insignificant. And even the signs, if the 25 was negative, that becomes insignificant. It's just you get a bigger number. Whether this bigger number is positive or negative, it doesn't matter. You get really, really small values getting close to 0. It doesn't matter whether they're positive or negative. Right. The only way the sign would matter would be if the numerator had the larger number. And we'll look at that on number 4. As x goes to infinity, the numerator function has higher degree than the denominator function. The ones after it become insignificant, so the numerator function is dominating the behavior, and this thing has, there is no horizontal asymptote if the numerator is higher degree than the denominator. All right, it's time for a break. Let's start again at 12:53 p.m. I'll see you in 15 minutes. All right, we're going to start up again. And all right. We have the last one we looked at when the degree of the numerator was larger than the degree of the denominator. We had no horizontal asymptote. And let's look at number 5. When the degree of the numerator and the denominator are the same, 5th degree. What happens as x gets super large, the other terms become inconsequential. This goes away. This goes away. This goes away. This goes away. As x gets super large, these dominate the behavior. Now suppose x is 1,000,000. X to the 5th is 1 with a tremendous amount of zeros, times 12, so it's 12 with this huge number of zeros. This is 3 with exactly the same number of zeros as this one. And all those zeros will reduce, and you'll get 12 divided by 3. In other words, the x to the 5ths will reduce. And you'll wind up getting this limit is 4. And we say when the degrees are the same, that the answer is the ratio of these leading coefficients. That's the leading coefficient of the numerator. It's the coefficient of the term with highest degree. That's the leading coefficient of the denominator. And the ratio of those is our limit. And in fact, this is the only way that you can get a non-zero horizontal asymptote, is if you're using polynomials. If the polynomial on the top has exactly the same degree as the polynomial on the bottom, then you're going to get the ratio of those. And so all of this is summarized in the textbook. Let's go back to the textbook, and it's on page 97. And this theorem, in behavior and asymptotes. So it says if you have a polynomial where a polynomial p sub x divided by q sub x, so that's your function, if the numerator has less degree than the denominator, then so the denominator dominates and your horizontal asymptote is y equals 0. Remember, vertical asymptotes had an equation of x equal a number. Horizontal asymptotes will have an equation y equal a number. If the degrees are equal, you get y equals the ratio of the leading coefficients. If the degree of the numerator greater than the degree of the denominator, so the top one dominates, then you go either to positive infinity or negative infinity. And then the next page, it talks then about slant asymptotes. And now m, let's go back a second. M was the degree of the top one of the numerator. And n is degree of the bottom one. So if the top one is 1 larger than the bottom one, only if that's the case, then you don't have a horizontal asymptote because the numerator dominates, but you can get a slant asymptote. And we won't emphasize slant asymptotes. I'm just going to briefly mention them. But that's only when the numerator is 1 degree higher than the denominator. And a quick example with a slant asymptote is if I had y equals 8x 6 minus 2x to the fourth plus 3 over over 4x to the fifth minus 7x plus 1. Okay. Now, this numerator is 1 degree higher than this denominator. And if that's the case, then you're going to get y, if you take the ratio of these things, you're going to get 2x when you reduce. Suppose you eliminated everything else, and then you reduce. Now, technically speaking, to find a vertical asymptote, you're not supposed to reduce like I'm doing right here. You're supposed to do long division, because you might get like y equals 2x plus 3 or something like this. But I made a very simple function that I knew wasn't going to have a plus 3 or some constant afterwards. But we're not going to go into horizontal asymptotes in detail here. So what this is saying is, now if I graph this function, y equals 2x, it goes to the origin with a slope of 2, something like this. This function is going to get infinitely close to that as x goes to infinity. So it doesn't have a ceiling, but it goes off to infinity in a kind of predictable way. And all right, that's the bulk of this section here. There's one other thing that I want to show you. If we take one of these problems and do it again, let's take number 5. Okay, Control C. Let's do this one more time. There's a way to do this, and I'm not going to require you to do this, but I want to just expose you to it. A way to do these kind of limits, it's a little more systematic. It's the limit as x approaches infinity. What you do is you find the highest, you divide everything by the highest degree of x that occurs in the denominator. The highest degree of x that occurs in the denominator is right here. So we're going to multiply this by 1 over x to the fifth, and we're going to multiply this by 1 over x to the fifth. And if you distribute the 1 over x to the, now it's always the highest degree that you find in the denominator. And if you distribute this through and then reduce, well, let's distribute it first and then not reduce. It'll be 12x to the fifth over x to the fifth plus 6x squared x to the fifth minus 7 over x to the fifth. In the denominator, okay, so let's continue. limit as x approaches infinity. This fraction reduces to 12. This fraction reduces to 6 over x cubed. This one is minus 7 over x to the 5th. In the bottom, you get 3 minus 4 over x plus 8 over x to the 4th. All right, now, as x goes to infinity, 12 stays 12. There's no x's in that term. This term goes to 0. This term goes to 0. And so on. So what we get is the limit x approaches infinity of 12 over 3. But x is no longer involved, so it's just 4. And so you can do that with any of these problems, and it kind of shows a bit more explicitly in a kind of algebraic way why these answers are what they are. And this one you'd multiply top and bottom on number 4 by 1 over x to the 2nd power. On this one you'd multiply top and bottom by 1 over x cubed, and so on. And it would work out, and it would be able to show what the answer is in a more algebraic manner. So if you prefer a more algebraic approach rather than saying, oh, the numerator denominates or the denominator dominates or something like this, you can use that to justify your reasoning. All right, and one last thing in this section, I want to cover 2 types of discontinuities. When you are making a function, you can have a discontinuous function a couple of ways. And let me just jump, hold on a second, let me see if, yeah, okay. All right. One type of discontinuity is if I'm drawing a function and I go from here to here, if you had to give this a name, what would you call this type of discontinuity? You're coming along and all of a sudden you go up to here. Anybody?
Jump discontinuity?
This is called a jump discontinuity because you jump in level. There is another type. Coming along, and at one particular value, it has a different value instead. Anybody have an idea? What would you call this type of discontinuity? What would seem natural to you? It's called
That removable?
removable, and another name for it that I like even better than that It's called a hole. Discontinuity. And it's also called removable. There's just a hole in your graph somewhere. And, all right, both of these ideas take us into the next section, which is on continuity of functions. Before I go there, is there any questions anybody has on 2.5? All right, let's go to 2.6, continuity of functions. And there's an intuitive definition. Over an interval along the x-axis, when we draw the function f of x, the definition of continuity is don't lift your pencil. If you can successfully do this, then the function f is continuous over this interval along the x-axis. So a picture might look like this. Along the x-axis from here to here, if when I'm drawing my function, I never have to lift my pencil, then from here to here, it was continuous. If when I was drawing, I had to lift my pencil, then it's not continuous. Okay. Now, that makes a whole lot of sense. Lifting your pencil or not for continuity of functions. But in math, we wind up having to describe continuity not just over an interval, but at a particular point. So, we come down to this question. How can you possibly define continuity of a function f at a single point? Let's say at x equals c. So, definition. Let f of x be defined on an open interval containing c. Now this open interval might be from a to b or something like this, or any open interval containing some point c. Maybe c is somewhere in here. We say that f is continuous at c if, and here I have a blank, and we're going to use one of our ideas that we've previously come up with in calculus, and it's going to fill in this blank. So it's been in one of the sections, and I want you to brainstorm in your group for just a little bit here. What in the world, how could we define being continuous at a point C using one of the ideas? We haven't had too many ideas yet, but one of these ideas, you know, all these titles over here, one of these ideas in these titles is going to relate right in here. And discuss in your group briefly, and I'll call on a group in a minute. How might we get one of those ideas relate to continuity at a point?
Can you repeat the question again, Professor Shankin?
All right, it's what's going to go in this blank on the definition. Let f of x be defined in open interval c. We said f is continuous at c if what's true. And so basically it's how do we define continuity at a point c? At a single point. Let me give you just a few more seconds, 30 seconds more. Darshan, I think your mic is still open. All right. Group 4. No. Group 4 I called on. I think. Yes. Group 5. Any ideas?
This is Dominic.
Hey, Dominic.
Um, uh, if a function is continuous at a point at point C, if the values of that point are the same as the limit at that point.
Yes, you are getting it. Okay. So the one idea that we're going to need over here is the limit idea. And so what we're going to fill in this is, and you can go ahead and close out your mic, Dominic.
Oh, sorry about that.
No problem.
I pulled a Sedacian.
Yes. If the limit, I'd put this right above this, except there's not much room. If the limit as x approaches c of f of x is the same as what we would get at the function. Now, how do you say that it's the same as what you would get at the function? So the left limit and the right limit have to be equal to the thing, and it turns out to be f of c. That's what completes this. If we use the limit idea, then we get continuity. Now this is extremely deceptive. This means 3 things. So I'm going to put this here. Note. This really says that there are 3 conditions for continuity at a point C. Condition number 1. It's a lot that this one little equation is implying. The first thing it is implying is that f of c, f of c, when I hit equals, now in Word it would do that a little bit better. F of c exists. So sometimes the function doesn't exist at f of c. For instance, you could have a function, here is c, that has a vertical asymptote at c. Then f of c doesn't exist. You could also have a function that just has a hole here, and there's no filling in the hole anywhere else. F of c has to exist, and that's implied in that statement. Number 2. The limit as x approaches C of f of x exists. Now, what this is really saying is both one-sided limits equal the same thing. Because if you have a limit from the left, different than the limit from the right, then this whole left side of this equation doesn't exist. And number 3 is that they are equal. So you just have the two things, f of c and the limit of f of c, they have to wind up being equal to one another. Alright, so I'm going to draw you a picture, and it's going to be not continuous, and you're going to have to look at all 3 conditions, and some of the conditions will probably be satisfying, and some of these 3 conditions will not be satisfying. It's discontinuous, and you have to state which one is satisfied and which one is not satisfied. Or just say which of the 3 conditions fails, because it's discontinuous. So, the first function, down here, number 1. So, here's my graph. Open circle here, and right above it there's a filled in dot right here, and that's right above 2. Okay, so state which condition is failed, which condition fails, 1, 2, or 3, or maybe more than one of these conditions fails. So go ahead and discuss that briefly in your group, and I'll call on a group in a moment. All right, group 6. Which condition fails?
Number 3.
Okay, you're saying that condition 1 does not fail. F of c exists. Yes, it does exist, because here is f of c, whatever that height is. And
Would say
the limit exists. The limit from the left and the limit from the right are both this height, whatever that height is. But they are not equal to each other. The only thing is it fails number 3. That is correct. All right, let me give you another one. Which condition or conditions fail for this discontinuity at, let's call this C, at x equals C? right, group 2.
We said it doesn't meet condition 2 and 3.
All right, let's look at all 3 of these conditions. Does f of c exist? Yes, f of c is this height right here. So it meets condition 1. And then does f of c, the limit as x approaches c of f of x, does that exist? No, because one limit is up there, the other limit is down here, so it fails 2. And then, since one of them doesn't exist, they can't be equal to each other. So you're exactly correct. Fails 2 and 3. And one more. Suppose that value is c. There's a discontinuity at x equals c. Which of the 3 fails? Give me a moment. All right, group number 3. What do you have?
I said all of them failed.
That's all, they all failed. F of c doesn't exist. The left limit and the right limit are different, so that limit doesn't exist. And then 2 things that don't exist can't be equal. So all 3 fail. All right, and let's look at some properties of continuity. And let's go to page 105. All right, so again, everything that we examine, and we get you used to this way of thinking, is we look at the properties of this new thing, and we have this new idea now of continuity. It started with this intuitive sense of, can you draw it without lifting your pencil? And then we saw that we could define continuity at a single point if we incorporated the ideas of limit into it. But how continuity works is if 2 functions f and g are both continuous at a point A, then also when you combine these 2 functions in any of these ways, you'll still get a continuous function. And you see, like by adding them or subtracting them, etc. And dividing, provided the denominator is not 0 when x is a. Okay, so now also, if you're reading the textbook, you notice that they have these things about to prove the first result. And that's the way of mathematics. It's very different than any other subject. Is we prove our results, and then once we've proved something, we call it a theorem, and then we get to use it like it's a basic fact, and then build off of that. And so even things that just seem kind of obvious to be true, we often will prove them. Okay. And polynomials are all continuous, and then you got to watch out where the denominator is 0. Composition of functions are continuous as well. And then there's another topic, the intermediate value theorem. Okay, and if you're reading the textbook and you read proofs, you'll wind up seeing the intermediate value theorem show up quite a bit in other proofs. So if you're not one who's reading the textbook, you don't need to know so much about intermediate value theorem. But in case you are, The intermediate value theorem says, suppose f is continuous on an interval a to b, and L is a number strictly between f of a and f of b. Then there exists at least one number c in AB satisfying f of c equals L. Now, if seen in the right way, this can make a lot of intuitive sense. But sometimes when you read something like this, it can take quite a while to figure out what in the world is this really saying. And let me give you a moment in your groups, and I'm going to pick on a group, and I'm going to ask for the group to state this in their own words, non-math lingo. What's the essence, the basic idea behind this? And then we'll see if we can kind of work our way towards simplifying this into non-mathematical language. So let me give you a minute on this. It's a very important skill here of learning how to get the essential idea of something.
Mr. Shankin, can you repeat the question?
Okay. The question is, state what this intermediate value theorem means in your own words. What's the idea behind it? The main idea. All right, let me have you stop. Let me go to group 6. What do you got for main idea? You can always say pass if you got no clue.
Would say if there's one number in a set that corresponds to another number, one number will exist.
Repeat that again.
If there's one number in a set that corresponds to another number, then that other number will exist.
I think you're getting at it. We're going to take that language, though, and we're going to put it a little simpler yet. Okay? And let me go to another group. Group 3. Any idea?
I said it was like a tangent line. So C would be the tangent of f of A to f of B.
You're trying to put the ideas together from our previous sections. Perhaps this has something to do with a tangent line. I like that approach of trying to integrate these ideas. But in this particular case, it's not going to have anything to do with tangent lines. But very good trying to put together the ideas. Let me go to group 5. What do you got?
This is Dominic. I'm stumped on this one.
Okay. Okay. And how about group two?
You said that
All
at
right,
least
Dominic, I think maybe your mic is still open.
Sorry about that.
Go ahead and Troop.
you said that there is at least one value within A, B that equals the value of L.
One value within A, B that equals the value of L. That is correct. All right, you're getting to the main point, and the idea is, let me put it down as well as can't jump over outputs with continuous functions. So, let me give you an example of what this might mean. Suppose the temperature at 3 p.m. on a very cold winter day is 0 degrees. And at 4 p.m. the temperature is 4 degrees. Now, we might ask this question. Was the temperature ever... Now, there's somebody else who's got a mic open. Let's just look real quick. Anybody?
Kylie.
No, I have push to talk. That was Bianca. She fixed it.
Yeah, Bianca fixed it? Okay, great. Thanks. Was the temperature ever exactly square root of 2 degrees between 3 p.m. and 4 p.m.? Now, when I say, is the temperature exactly square root of 2 degrees? Square root of 2 degrees, we can't even write down the number square root of 2 exactly in a decimal format. If you do, you have to write forever, and you'll never get into a repeating pattern. So, was the temperature ever exactly the square root of 2 degrees between 3 p.m. and 4 p.m.? The answer to that all depends on your assumptions that you make. And if you assume that temperature was a continuous function, then let's look at this theorem in the light of that problem. This then would be the time of day. This could be 3 p.m. This could be 4 p.m. This could be 0 degrees, so this would be temperature. This could be 4 degrees. And then some value in between. Does it pass through every single value in between? Well, one of the possible values in between, no matter what it is, if that number is between 0 and 4, this saying, if it's a continuous function, it has to pass through that value. So we would say yes. We don't know what time it is, but at some point in between 3 and 4 p.m., there had to have been there exists at least one number C in AB satisfying f of C is equal to L. If L is strictly between Now, strictly between means not the smallest and not the largest, but strictly between them. There must be at least one number that satisfies that. So there must be one time where it was exactly square root 2 degrees temperature. And again, the answer depends on our assumptions. And in the world of physics, is temperature really a continuous function? What do y'all think?
I say no.
Yeah, I agree. It's too hard to get that close to numbers in the real world. There's too many other variables to count.
Yep. In the world of physics, it does appear to be the case that, and it's a quantum theory, that even energy comes in small little packets, and there's the smallest undivisible packet of energy. And so it's not really exactly continuous. So when we make these kind of assumptions for something in the physical world, we might want to examine those assumptions really closely. If we say, temperature seems like it's continuous, but in actuality it isn't exactly continuous. So that covers all the ideas for today.
So
Yes.
I have a question.
Mhm.
So would this example kind of be like the graph for the second graph if you were to use it as an example instead of the first one?
Yes. Now this example could be like, now the earlier time it was a higher temperature, 3 p.m. it was 4 degrees, and at 4 p.m. it was 0 degrees, and the temperature became cooler and then got hotter again and then became cooler, and so 3 different times it had the temperature of square root 2 degrees. So at least once it's got to happen. You can't get from here to here without crossing this line. At least once. You might cross it multiple times, but you have to cross that line at least once if you're a continuous function. Does that make sense, Kylie?
Yeah, so if there was a horizontal asymptote that it doesn't cross, does that mean that it doesn't? Well, that would still be a continuous line, right? It would be a continuous function, but
Yeah,
since
if you
it
have a
doesn't
continuous
cross,
between 2 points, yeah, we wouldn't really be concerned about horizontal asymptotes there because that's going off to infinity, way far to the right. This is more like if you're confined between A and B, between 2 specific points along the x-axis.
oh, okay, that makes sense.
Any other questions? Good question. And Kylie, you're continually trying to relate things to other stuff that we learned, which is exactly the kind of thinking we need in this class. And all right, so the homework is we did 2.5 limits at infinity, and we did 2.6 continuity of functions. So the spot check tomorrow is for both 2.5 and 2.6. Have at least 75% of each of those done. And I will see you all tomorrow online. And I'm going to remember to stop the video.